Okay, do you have your presentation in the language? Okay, he's okay. I think we can start, right?
Okay.
Yeah. Good morning, thank you for coming such early times. I'm Saeed Al-Khaled, I'll be co-chairing with Edwin. I'm the Chief Data Scientist at Global and a research professor at the University of Illinois Chicago. It's my pleasure to introduce Professor Edwin Su. Edwin got his birthday from Hong Kong University, but he worked at Berkeley, and patent experimentation. And I believe that your research mostly focused on heat transfer material within the
Exactly.
Thank you very much.
Thank you. Okay, thank you, Sai, and thank you everyone to come such a morning. And I'm Edwin from City University of Hong Kong. So today I would like to talk about my research, part of my research area. So focusing on building energy related incidents. And also very honored to be invited as a keynote speaker for this MIT24 conference. So as we all know, our Earth is getting sick and the temperature keep going up, and we're also suffering some really unemployment cities. And for the individual person, some of us may suffering from the heat-related illness, and at the end will lead to the lower efficiency, and it actually at the end will cause health, economy, and environmental crisis. So to solve this problem, and particularly in Hong Kong, maybe some of you went to Hong Kong before. Hong Kong typically maintains the subtropical climate, and we suffer very hot and humid climate in summers. The temperature can go up to like close to 37 or something. The humidity is very high. So because we have a lot of buildings, receive a lot of energy, and when we have all 50,000 buildings together, but in a very dense area, like a 230 kilometers square. So we are currently staying in a very extremely dense cities. And if you sum all the heights of the building together in Hong Kong, it typically is around 40 times of the height of Mount Everest. So we have a lot of. So definitely, in Hong Kong, building consume more than 90% of total electricity. And from those 90%, air conditioning actually occupy the most. No matter for the residential or commercial buildings, the energy consumption due to the air conditioning consume nearly 50%. This is typically due to the high window to wall ratios, particularly in those commercial buildings. So to solve those problems, I come out all-in-one building energy solution that is lies in my research areas. The first one is we call it from a smart window that is to be used in the transparent part of the building. That's to mitigate the heat gain from the surroundings. And for those building effluent, that is opaque part, transparent parts, that's I propose to have the better radiant cooling, have a key cooling purpose. And then we also need to have a control system. I think develop model control scheme that will control the traditional HVAC system with the new technology like the smart window and better cooling. So in this way, we can further save the energy of traditional air conditioning because we adopt a new energy efficient technologies. And then the later part, some of my students and postdoc are working on some building scale assessment. That is how we got one into similar study. If we integrate those new technologies like the smart window, better radiant cooling together into the existing building, with say for example the solar panels, what are the performance? I think that we also provide very comprehensive building performance evaluations. Finally, we not only look for the building itself, if we have a lot of buildings together in the community or in the city, how those kind of new technology can mitigate the urban impact. This also I would like to and we often get some effect result from the using the radiant cooling in the community, the city scale to mitigate the urban effects. So now I'm going to first talk about the smart window parts. So what is promote smart window? I think maybe some of you know the electronic smart window that is currently commercialized in voice and A7. Plus that window we need to use electricity to trigger the temperature transmissions. For the promote smart window that is totally passive. We utilize temperature to trigger the thermochemics. That means when the temperature is low, the window is just like a normal glass window to allow the thermal radiation to get in. When the ambient temperature is high, the window will start to absorb a part of solar radiation. In this way, you can reduce the indoor air temperature for indoor air cooling or heating methods. So I have the thermochemic smart window since 2018. When I back from a respect group back to Hong Kong, I focused on stuff from the VO2, and then later on involved on the perovskites. So most of the scientists doing perovskite is actually focused on the perovskite solar cells, but I found that for some of the organic perovskite material that also have a thermochemic effect. So I started to work on the perovskite thermochemic material and publish different kind of paper in Nature Advanced Material and so on. So I will do my research here in relation to the thermochemic perovskite materials. So this is the first perovskite thermochemic material that our group developed in 2018. That is, we use MIT24, that is a typical 2D organic perovskite. And when temperature low and the transmittance is normal transmittance is about 85%. For the traditional window, the transmittance is about 90%. So it's typically very close to the normal glass window. But when it goes up, the luminant transmittance and the solar and the visible region will drop to 30%. So like this way. And leading to the solar motion ratio of about 23%. So and we can also adjust the material composition. We can control the color of the part of the material, and the temperature can also be controlled within about 25 and 45 degrees Celsius. And the whole transition process can be finished in a few couple of minutes. However, for this kind of the perovskite material, there's a very fatal issue that in order to trigger the thermochemics on the material need to be controlled within a very precise period. That's around 20% or even lower. So that's why if we want to in the commercial students, the only way is to put this perovskite material thing in the double grace window, such that we can control the humidity inside. But indeed, as a result, the installation and the maintenance cost will be very high. So to solve this problem, that we come out the second perovskite from the perovskite window. Very simple. The short term we call the near infrared active from the perovskite smart window. The short here is TPCL. As we typically break the CWO thermochemic coating together with slowing coating to the window, forming an optical layout window. In this way, the significance is the window and the near infrared region is start to absorb the radiations. So you can see from the last window that's in the near infrared, we still have a very high transmittance. But after adding the CWO, the near infrared region will start to absorb the radiation. In this way, the material itself can absorb the radiation, and then even the humidity is about 50–60%. We can check that from our conversations. So this is sort of the period problem of perovskite material. So you can see that even under 0.7 some, the Windows temperature can reach about 40 degrees Celsius trigger transition temperatures. And then maybe you may argue that the window itself may be very hot after absorbing the near infrared. So that's why we also let a low coating to prevent the in this way the window itself will not emit the radiation, second the radiation to the indoor environment. So you can see the emissivity in the mid infrared region of this TPCL window is about 27%, which is very low and close to the low E windows. So we have conducted a model house for built 4 model houses. The first one is normal glass window. The second one is the low E window. The third one is the window. This window, but without the low E coating. The last one is TPCL window. And we conduct a few things in a local Hong Kong climate, and we found the indoor air temperature in the model house is about 80 degrees Celsius lower than the normal glass window. We can save about at least 10% of energy consumptions. So, but this kind of window, there is no matter perovskite, if you are talking about the perovskite solar cell, whatever, another thing we usually is the stability in the line space. So how to solve it? Typically for this 3D perovskite material, the lifespan is around a couple of days, 2 or 3 days, and then after that, the thermochromics effect hopefully disappears. So to solve this problem, our team actually recently published in the Nature Communications that's inspired by the face mask that will be wearing every day during the pandemic period. Because for the face mask, we have 3 layers. The outer loose layer actually is to repel the bacteria and allow a certain amount of air to into our lungs. So similarly, we also have 2 more layers. The outer layer is to repel the water droplet. The middle layer actually is to allow a certain vapor to transmit, because we need the water vapor in to react with the perovskite material such that perovskite can conduct the exchange. So we do not want to have enough water droplet. We indeed need to have some water vapor. So in this way, we put up 2 extra coating. One is PHBS coating. The other one on top of the PHBS coating is silicon dioxide nanoparticles. So in this way, we can achieve a very super hydrophobic surface with over contact angle over 160 degrees. And you can see that no matter in the cold state or hot state, the water droplet actually totally repel. The water vapor, a small amount of water vapor can penetrate into the perovskite to trigger the thermochromics. So in this way, we can find that this is a cold state, this is a hot state. The transmittance at cold state can still keep at about 80%, hot state at 30%. And leading to about 104% solar motion ability. The most importantly, the haze of the window is dramatically reduced. This is the previous common perovskite window with a high haze that we cannot see the object behind the window. These 2 layers, we actually, because PHPS layer as an optical buffer layer can reduce anti-reflection layer, can reduce the reflection intensity and the diffusion. In this way, the haze will be dramatically reduced from 19% to like 30%, so we can see the object clearly. So how about the durability and lifespan? So the previous perovskite materials, the lifespan, you can see that after 1 day, the thermochromics actually totally disappear. And even maybe after 5 days, there's no thermochromics effect. However, after these 2 layers, we can extend the lifespan by up to 1 month. So this is the one of the greatest achievement our work to identify how we can extend the lifespan of the perovskite material such that in the near future it can be put in the commercial. And then perovskite on the other hand can generate electricity. So that's why we recently come out with the idea that this perovskite material typically can generate electricity at the hot state if we add some electrolyte and transport layers. So, and we also had during the fabrication process, we found that if we're using anti-solvent solution during the fabrication, we can further reduce the haze to 11, even lower than the previous one. And the morphology of the window material is highly improved. It's significantly enhanced. This is the SEM photo showing it's very smooth morphology of the coating after using anti-solvent method. The roughness surface is reduced to 7 nanometer. If we do not use anti-solvent method, previous morphology is very high, and also the roughness is about 220 nanometer. If we do not have a very plain morphology surface, even with some electrolyte, windows are considered to generate electricity. So that's one of we need to solve the morphology. To solve the morphology, we added electrolyte and we can successfully demonstrate 2% power conversion efficiency at the hot state. I think this is already the record high power conversion efficiency for the perovskite from perovskite for window application so far. And we can achieve not nearly 90% solar lumen transmittance at cold state and 19% at the hot state, leading to a record high solar motion ability, which about 31%. This is the highest record that we can box in terms of solar motion ability for the from common perovskite material. So you can see from these two figures, compare all the previous perovskite material for the chromatography. Our work leads to the higher fluorogenability and the lower now, of course, the highest normal transmitter in the cold states. So then for the part like the whole big like a roof and the wall of the building, as we would like to introduce the passive radiative cooling, which is recently a very hot topic. So I work on the say actually passive radiative cooling is inspired by nature. Why Sahara supernatant? It is surviving for Sahara nature because of their particular structure can radiate effectively strongly reflect solar radiation simultaneously with the heating radiation to the whole universe. So, and the working principle is very simple to achieve the radiative cooling. First, during the daytime, we need to strongly reflect solar radiation from the sun. And then get the 8 to 30 micron, we need to strongly emit the thermal radiation to the whole universe where the temperature there is 0 Kelvin. So in this way, we can passively generate some cooling effect. And then the work actually I started when I was still in the UC Berkeley working with my supervisor Professor Chris Sams there, and then come back to Hong Kong. I keep working on the passive radiative cooling, but start from the photonic-based passive radiative cooler. And then later, because but the photonic one is very expensive in terms of manufacturing and difficult to be in a larger scale. So later I moved to polymer and microchannel inorganic coatings. And recently our work has been preparation science about the widest fluids along in the wall that we can achieve solar reflectivity of 99.6%, which already shown a record. Solar reflectivity and also the highest passive radiative cooling power, which is already almost reached theoretical maximum cooling power is about 140 watt per meter square. So in today's talk, I will emphasize to spend more time to talk about what we have conversion science. And so well, not too bad. The previous paper covers about passive radiative cooling. You have the passive radiative cooling wall, passive radiative cooling whole tanks, etc. etc. Well, to my and I found that actually the facade and the building wall actually is not made by the coatings, actually is installed by a lot of small pieces of ceramic caps. So that's why it inspired me and come to the like student is waterproof. We can build a ceramic cap that actually has a very high solar reflectivity and high resistivity. So when we have this idea, go to the left. And we have we choose aluminum oxide particle, which is a metal oxide material. It's very abundant in the world and very cheap. Then and also the reason why we like to use ceramic because for most of the passive radiative cooler built before actually they use polymers. As we know for polymer, if we put our wall for like 1 year, it must have a strong degradations. And then we like so the polymer will become very brittle at the end, and the wrinkle will become first will become yellow and then become brittle. So the like polymer material is difficult to sustain outdoor environment. If we're using metal oxide, which is inorganic material, typically we can solve the problem of the UV degradation problems. So that's why we have chosen aluminum oxide, and we have optimized the hole distribution and the size of holes. We can achieve the highest 99.6% solar reflectivity with also very high resistivity in 8 to 30 micron, which is about 95%. And we have conducted a few tests in Hong Kong first, and we can continuously monitor ambient cooling as the cooling ceramic house temperature itself is around 4 degrees Celsius lower than ambient temperature. Then we compare to the commercial white tiles, we can achieve like 8 degrees Celsius lower. And then we have also conducted measured the cooling power. So we found that with extremely almost ideal solar reflectivity with 100%, we have achieved the data of cooling power 134 watt per meter square, 140 watt per meter square, almost reached the theoretical limits. And we also go to different cities to study the various climate conditions to the cooling effect. And we almost no matter in which kind of the city, including Boston, we have done 2 years ago, and then we can achieve secondary cooling. And then we have built 2 separated house, model house that's on the rooftop with about 50 square feet. Here we have more than 200 pieces of our small ceramic tiles we made by our lab and compared to the commercial white tiles. So from appearance, from by our naked eye, there's no difference. Both are not very nice. And we install based on the ceramic tile to replace the rooftop. And then inside each model house, we put 1 air conditioner in each model house. And this time we do not measure the indoor temperature readings. We directly record the power consumption of the air conditioner directly to see the energy consumption. And then of course, is well suited to prevent any conversion loss. And then we found that we continue to monitor for a couple of days, and then we found every set different temperature of the air conditioner. Say for example, we set at 23 degrees Celsius, which means when the indoor temperature is higher than 23, air conditioner will switch on. Below 23 will switch off. So in this way, in general, we can achieve, let's say, about 20% electricity consumption directly from the air conditioner. And this is the one of the research in the paper. And then we can also demonstrate different color. We demonstrate yellow, red, gray, and black. So we can show in different shapes. This is actually can be replaced for the existing tiles in the market. And even for those carbon ceramics, the reflectivity is at least 10 or 20% higher than the existing color commercial tile with the same color index, but our reflectivity is higher. And then and also in terms of dust resistant tests, we also perform if we put outdoor and to see if there are a lot of dust, where the dust affects solar reflectivity. And we found that when we do the self cleaning, then reflectivity will be recovered back to around 90%. So if the dust will not fail. And the most importantly, we put our cooling ceramic outdoor naturally for 1 year, over 1 year, and then we measure the solar reflectivity. Again, you can see the green line that's the solar reflectivity drop lower than the original before the outdoor exposure, but the overall drop is only about 1.5%. So later on, it still can keep like 98%. So this again to prove that the metal oxide material has a very strong effects against the degradation of the UV light. And this another spotlight of this paper that is collaborated with my colleagues, Professor Wang Zhengkai, that's we found that after adding a special layer of the coating, the cooling ceramic will become completely super hydrophilic and it can solve the problem of the latent force effect. So what is latent force effect? Typically when you cooking, during cooking, the pan is very hot. So you must put some water on the very hot pan. The natural phenomenon is the water will jump on the hot surface like in this way. So because there exists a lot of air layer between the drawback and the hot surface, so it leads to a loss efficient cooling actually surface. So this problem is we call the latent force effect. But after we found my collaborator after adding the material coating on the cooling ceramic, and we found that when we drop that into our cooling ceramic, totally super hydrophilic, the water will totally absorbed by the surface. So in this way, we can use the evaporative cooling effect to totally reduce the surface temperatures of the cooling ceramic compared to the commercial tests. So this is another brief flow. These 3 hours show another functionality of the cooling ceramic, and another functionality is the material actually totally really can and recycle and to do again we can find another cooling ceramics. So and recently we are working on the cooling tower control for the passive radiative cooler. That's because you know for those cooler if we have if we utilize in some cold climate like in Boston in winter, it will be very extremely cold. So in this way, we will have cooling penalties. So which means in winter when you will need to switch on the heater and provide extra heating energy. So this is the problem that we like to solve. And to see whether we have some cooling power control the pressure reduced cooler. So we have developed a multiple layer cooler. There's a top layer we call the TAM that can go up and down due to the solar intensity initiative, and then the bottom layer is the normal pattern related cooling. So in this way, when the ambient temperature in summer, when the solar intensity is high, the material roll up. So the bottom related cooling will directly face to the sky to perform a related cooling. When in the winter, with a not very strong solar intensity value, the top layer will lay down and cover the bottom related cooler and to perform the solar absorption to keep the building warm. So we have demonstrated this kind of coating is also flexible, and we have conducted a few tests in Hong Kong in summer that we can reduce ambient temperature about 9 degrees Celsius. But then we go to Changchun, it's a northern part of the city in China. The coating has a higher temperature than the ambient by about 9 degrees Celsius, which can perform the normal coating functions. And then the third part is due to the time issue, our team is also working on the model predictive control, which is AI control system to integrate the periods to material together with the existing central air conditioning system. That we know that if we control the envelope is to absorb less energy or emit more energy to the universe, indoor air cooling system may be reduce the heating cooling. So we need to have control between the new system, the air conditioning system through control from the waters. And then we like to talk about scale assessment. So this is another part of my research is working on that how to utilize those kind of renewable material and hydrogel based for smart windows. In the existing window, for example, we have a different kind of window structure like a single glaze, double glaze, vacuum glaze, ventilation glaze. If we put those new materials into this kind of structure, they are still unknown how they perform. So we have conducted a model, energy cost model to estimate the energy thermal comfort, energy usage, and the virtual comfort after using those common material. And then the result shows that the vacuum windows that's in this way can show the highest energy saving, the best visual comfort, and also the best thermal comfort. So this is another study that we are working on. And then we also working on pattern related cooling combined with some traditional phase changing material, combined with paraffin wax, and to because the existing passive phase changing material, phase changing rooftop is lack of significant cooling capacity, and the performance may be even weaker when the PCM is fully melted. So we propose to combine the PCM together with the passive related cooling on top of PCM and to in the building application. We have developed a two-quarter related cooling and a phase changing material model, and the model is validated by the experiment, and we found that with this novel related cooling PCM roof, we can reduce temperature by 28 degrees Celsius, saving reduced total energy heat gain by about 170%. And the best melting temperature of the phase changing material should be optimized at about 21 degrees Celsius in Hong Kong's climates. The last is about the urban heat island application, as I just mentioned. That's my goal is also to study if not only single building utilize the thermochemical related cooling, but the whole community, whole city utilize this related cooling technology, whether this kind of technology can help to mitigate the urban heat island effect. So this is the question that no one has actually studied on this. So my team will be the first one to work on that. So we have the urban canopy model together with the related cooling model. This is the building heights, and this is the canopy, the streets. And then we have also, of course, we have conducted experiment in Hong Kong. We call a very large area with more than 10,000 square feet area in Hong Kong, and to verify the model. And then the model is after validates, and we can predict the effect of the related cooling on different temperature reductions. And also we have studied the cooling effect against the various height to wall ratio, which means in this configuration, that's two buildings are far away compared to these two buildings are nearby. If two buildings are nearby, that's which means some solar. If we use it radiative cooling, the effect will not that significant because some of the sunlight will be blocked by the building nearby. So that's why if we have a higher height to width ratio, actually the cooling effect will be reduced. And we have also applied the model in whole China, different city, and to see as if the whole China for the eastern part of the city in China utilize special radiative cooling, the city's temperature can be reduced by at least 15 to 14 degrees Celsius compared to the city that's without using special radiative cooling. So finally, I would like to spend maybe 1 or 2 minutes to talk about some knowledge transfer and empirical research from my radiative cooler to the society. Is how we impact the society and the world. That's I have co-founded a company called MIT24 2 years ago, and we have raised the funding of more than 18 million US dollar within 2 years time. And in the first year, half year of 2024, we have already got 8 million US dollar revenue selling the radiative cooling printing to different scenario. And one of the early investment, maybe some of you know that is Li Zheshan, which is the co-founder of the EJI, and also the Dr. Peter Lee, the chairman of the Henderson Land Developers. And we have applied this kind of passive radiative cooling in different scenarios, like agriculture, power stations, chemical plants, logistic containers, green storage, PV, because if we put radiative cooling together with the solar cell, we can improve the power conversion efficiency of the solar cell due to the temperature reduction. And also we have applied onto the bus. Room hall with our coating can save about 1 million per month. The payback period is about 1 year after a couple of months of trial testing. And we have already sell different products in different part of the city. Maybe the one important is Dubai Mall, which is the largest shopping mall. Then the next time you go to visit Dubai, actually the shopping mall there already have put our cooling coating from Dubai Mall there and can reduce more than 40 degrees Celsius temperature because you know Dubai is suffering very high temperature throughout the years. And we have already, and also we have applied coating in different GCC countries. So this is some media reporting my works. And finally, I would like to thanks to my teams. My team is over 100 students and postdoc and RAs, and also my collaborator, including different cities like Beijing, Tsinghua University, and NTU, and also the Polytechnic universities. Without them, I think my research works is difficult to be conducted in such a way. So this is the end of my presentation. Thank you very much. I'd like to take any questions from the audience. Thank you. We have time for questions.
I have a question. You mentioned that the coding can be used on its own for different applications. Do you feel that the adhesion to the various surfaces is a problem or something you
That is not a big problem because so far the longest application using our radiative cooling coating is more than 3 years. So after 3 years, even suffering from heavy winds, typhoon, outdoors, the coating is still strongly adhesive on the existing building rooftop because our coating actually is just similar to a normal coating from the industry. As we of course to utilize some particular material in this such that the solar reflectivity is higher than those existing materials, so the adhesions will not be a major problem due to our based on our application test for over 3 years in the market. Thank you.
Any other questions? Yes.
I just have a question. I mean, maybe this is a bit of a stretch, but have you sort of envisioned this coating technology as a part of any Peltier cooling technique? Peltier coolers, you know, where you're generating energy based on the temperature differentials between the two surfaces. I'm just kind of curious.
And if you make the very good questions, actually many of them, scientists for this discussion because actually we use universe for tuning. So, we will next the end will actually temperature of the surface cannot be something you need outside or brought by the nearby buildings will track the heat inside the community is the question you asked, right? So, so typically, so for this pressure relief, of course, the best application scenario is not in city that like Hong Kong, we have all high-rise buildings, and we recommend to use only limited to the rooftops. If we put on the walls, maybe if we have some solar radiation received and after reflection will cause some light pollution as well. So that's why initially our target application is building, but now when we sell cooling coating to the different industry, building is not our biggest revenues. Our biggest revenue is petroleum plants, chemical plants, grain storage, because those tanks is actually built outside the cities, outside the and it's very easier to measure the reflections because and for buildings human being is subject human beings, so that's we maybe you feel cold, maybe you feel very hot. But for those kind of the can of the petroleum can or whatever the storage can that we can directly measure the say for example chemical loss directly we will know after using the coating. So this is a direct so during the commercialization, the biggest revenue of this cooling coating the market actually is come from the storage tanks instead of the buildings. So and though actually those market is even larger actually. We don't know and before so that's why when we go to the market we talk to different people then we know that is a lot of people are interested in this coating in the chemical plants this kind of application instead of doing it's actually difficult because first and it's one of the issues. Some people may not want to have a white one, they would like to have some gray or whatever. So that we have some difficulty. But at the end, when we know that the we have cutting with oil. They are leaving to since to increase the market. Leaving because the leaving can receive less someone who gets so the markets going to move on. Yeah, thank you for your questions.
Okay, here you go. Well, thank you very much.